Hello, this is Abdul. In this video tutorial, we will solve three examples by using the monotone convergence theorem. These three examples are listed here. Let me first recall what is a monotone convergence theorem. The statement of the monotone convergence theorem is if a sequence an, the sequence is monotone, that means that it is either increasing or it is a decreasing, and this sequence is also bounded. The bounded means if this sequence is bounded above as well as this is a bounded below sequence, and this implies that the sequence an is convergent. CGT is the short form of writing convergent. I can also basically split this statement into two parts. In part one, if my sequence an is monotonically increasing, or in word, if the sequence is increasing, then I need to show, and if I can also show that this sequence is bounded above, because if it is increasing, all I need is, if it is a bounded above, then this will imply the sequence is convergent. Is convergent. So I don't need to show if the sequence is increasing, I don't need to show that the sequence is also bounded below. All I need to show is it's just bounded above. And in the second part, if the sequence instead of increasing, if I find that my sequence is decreasing, then all I need to show the next part is the sequence is bounded below. And then this will implies the sequence an is convergent. CGT is I'm using the short form for the convergent. Now let me consider my first example. So my first example is the sequence an is equal to n minus square root of n square plus 1. To find whether this sequence is increasing or it is a decreasing sequence, I will use my second method, which I showed you in my previous video. So for that, I will consider a function f of x is equal to x. I will turn every n into x, and I will see that whether this function is increasing or decreasing, because this function and the sequence, they will behave same. If the function is increasing, then the sequence will be increasing, and if the function is decreasing, the sequence will be decreasing. So we know from the calculus how to find a function is increasing and decreasing by calculating its derivative. So now I will calculate the derivative of this function. So here is the derivative of this function, and clearly this term is strictly greater than or is equal to 0. As you can see that also, like because x square plus 1 is always greater than or is equal to x square, because if you add 1 in the positive number, it will be also greater than. So if I take now the square root, so x square plus 1 will be greater than or is equal to x, and x is always a positive. Therefore, this term is always greater than or is equal to this term. So this implies the denominator is always positive, and we always has a denominator is positive. So this will be always greater than or is equal to 0. So this implies this function f of x is an increasing function. If this function is an increasing function, this implies this sequence, which is sequence an, is monotone increasing, or in other words, this is just monotone. Now, since this function is a monotonically increasing, all I need to show is this function is also bounded above. So it is, I need to find a number, so that I need to show that every term of this sequence is less than or is equal to that real number. Now let's show whether this function is bounded above. So first observe again, n square plus 1, it's always greater than or is equal to n. square, because if you add 1 in the natural number, the square of the natural number is always going to be bigger than that natural number. So if I take the square root of this, n square plus 1 is always greater than is equal to n. And therefore, if I move that term on the other side, so this implies n minus the square root of n square plus 1 is always less than or equal to 0 for all values of n belong to set of natural number. So this shows that each value or each term of the sequence, so this implies a n is always less than or equal to 0, that is the each term of the sequence is bounded above by 0. So therefore, this sequence is monotonically increasing, and also it is bounded above. Therefore, this sequence is by monotone convergence theorem. By monotone convergence theorem, this implies the sequence AN is convergent. Next, we will solve this example by using the monotone convergence theorem. In this example, our sequence is given in term of this recurrence relation. This time we do not have the explicit form of the journal term. Instead of that, our journal term satisfies this relation. And in this example, we will show that the sequence is bounded, the sequence is also monotone, and also we will find the limit of the sequence. So in other words, we have the 3-step for this problem to solve. In step number 1, we will show the sequence is bounded, and then we will also show that this sequence is monotone. And since if the sequence is bounded and monotone, it will be a convergent. If the sequence is a convergent, then we will also find what is the limit of this sequence. So these are the 3 steps of this problem which we will need to solve. So I'm going to start from step number 3, because the step number 3 will help me to solve the step number 1 and step number 2. So in order to do the step number 3, first I will assume that this sequence is bounded and monotone. So therefore it is a convergent. So by monotone convergence theorem, I can assume that the limit of this sequence as n approaches to infinity an is equal to L. And this is intuitively clear that if the as n approaches to infinity, n is going to L, if I take n plus 1 term of the sequence, this must also going to be L. Because if n is going to infinity, n plus 1 is also goes to infinity. Now, since I have this recurrence relation, a n plus 1 is equal to 1 half a n plus 4. If I take my limit n approaches to infinity on both sides, I will get L is equal to 1 half L plus 4. Therefore, the value of my limit is 8. So this shows that if my sequence is convergent, which I have not shown yet, then the limit of this sequence must be 8. Now let's show that the sequence is convergent. And in order to show this, we need to show that this sequence is bounded and this is a monotone. So in order to show the sequence is bounded, I'm going to compute first few terms. My A1 is 1. If I compute A2, I will get basically plugging 1 on this side. So 1 half plus 4 is a 4.5. If I compute A3, so A3 will be 6.25 and so on. So this shows that this sequence is increasing, and so if the sequence is increasing, we must show that this sequence is bounded above, because if the sequence is increasing, then the monotone convergence, the first part of the monotone convergence, we need to show this sequence is bounded above. And I will show that this sequence is, I'm going to claim this sequence is bounded above, and it's bounded above by its limit L. So this is the reason I compute my L first, so I can find what is the upper bound of that sequence. So now I will even prove this claim. So I claim that my sequence is bounded below and it's a bounded above, and it's bounded above by 8. And I'm going to prove this claim by using the method of induction. So in the method of induction has the 3 part. In first part, we show that a result is true for the base case. In this case, n is equal to 1. In the second part, we assume that a result is true for n is equal to k. And in the third part, we show that a result is true for n is equal to k plus 1. So let's check with the base case is true. So if a1, I compute a1, which is a 1, 1 is definitely less than is equal to 8. So therefore, the case is true for n is equal to 1. Now let's assume that the kth case is true, that the sequence, the kth term of the sequence is less than is equal to 8. That is, the result is true for 3. Now I will do some manipulation to this inequality and prove that a k plus 1 is also less than is equal to 8. So first I will multiply by 1/2 on both sides to this inequality. So I will get a k less than is equal to 4. And then I will add 4 on both sides. So therefore 1/2 a k plus 4 is equal to less than is equal to 8. But this term is from this recurrence relation is just a k plus 1. So therefore, what I have is, so this implies a k plus 1 is also less than is equal to 8. So by the principle of mathematical induction, this result is true, and this trust is true for all values of n belong to set of natural number. So this shows our sequence is bounded, and it is bounded above by 8. Now it is clear that the sequence is increasing if we compute few terms. And now we will rigorously prove that the sequence is monotonically increasing. In order to do that, I will compute a n plus 1 minus a n term, and I will show this term is greater than or is equal to 0. Now I'm going to use the recurrence relation and substitute the value of a n plus 1. So therefore, this is a 1/2 a n plus 4, and this is a minus a n. If I simplify a little bit here, I will get a n 1/2, the negative sign, 1/2 minus a n is a minus 1/2 a n plus 4. But we know that each term a n is less than is equal to 8. Therefore, so here, because a n is less than is equal to 8, therefore negative of a n will be bigger than is equal to negative 8. And if I divide by 2 on both sides, so it will be, this is a minus a n divided by 2 is bigger than is equal to negative 4. So I can use this inequality here. So this is a bigger than or is equal to negative 4 plus 4, which in fact is equal to 0. So this shows a n plus 1 minus a n is bigger than or is equal to 0, or in other words, a n plus 1 is bigger than is equal to a n. So this inequality shows this sequence is monotonically increasing sequence. So we have proved that the sequence is bounded, and also the sequence is monotonically increasing. Therefore, by using the monotone convergence theorem, this sequence is convergent, and we can safely assume that this converges to L, and then we also compute that values of L by using this calculation. So this complete our second example. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is our third example. In this example, we will also use the monotone convergence theorem to find the limit of this sequence. Again, in a similar way, I will prove that the sequence is bounded. I will prove also the sequence is monotone, and I will find the limit. since it is always helpful to find the limit first, so I will begin by calculating the limit first, and then I will show that the sequence is bounded and also it is monotone. So let's assume this sequence is convergent and the limit of this sequence is as n approaches to infinity. This time the sequence is xn is L. If I take my recurrence relation and take the limit on both sides, I will get L 1 half L plus 2 over L. It is pretty clear that L must not be 0 because L is in the denominator. So I'm going to move everything on one side and do a little bit more simplification. So this is a L minus 1 half L and minus 1 over L is equal to 0. And this can be simplified to 1 half L minus 1 over L is equal to 0. And this can be also written as 2L L square minus 2 is equal to 0. Therefore, L can be square root of 2, it can be plus minus square root of 2, but each term of the sequence is positive, so therefore I can safely say that this limiter must be square root of 2 only. So my claim is this is square root of 2. Next, I will compute the few term of the sequence. So let's suppose if I compute x1, which is equal to 2, if I compute x2 by plugging x1 in this recurrence relations, my x2 will be 1.5. If I compute x3, it will be something 1.42 and so on. So I can observe that my sequence is decreasing, and therefore, if I want to use the Monotone Convergence Theorem, I must need to show that this sequence is bounded below, and this is a monotonically decreasing sequence. So if I want to show that this sequence is bounded below, I think that must be the square root of 2 should be, it is a lower bound. So I will show that this inequality hold for all values of n belongs to set of natural numbers. Again, I will use the method of induction to prove this inequality, as it is clear that the base case is true if I calculate the term x1, which is a 2 given, and then this is definitely bigger than or equal to square root of 2. So the result is true for n is equal to 1, which is our base case. Now I am going to assume that my result is true for k case, or in other words, my xk term of the sequence is always greater than or is equal to square root of 2. So now I need to prove that xk plus 1 term, which is also can be written as 1 half xk plus 2 divided by xk. I need to show that this term is always bigger than or is equal to square root of 2. To prove this, I will use this very important inequality, which says that if you have two real numbers, the arithmetic mean of these two real numbers is always greater than is equal to their geometric mean. So x times y. So I will use this important result to prove that my sequence is satisfy that relation. So therefore, as you can see, this is the arithmetic means of these two terms. So it's 1 half this term plus that term. So this quantity, the arithmetic mean, must be greater than the square root of xk times 2 divided by xk. And now the xk will cancel out and you will get this is equal to square root of 2. So this proves xk plus 1 term is also greater than is equal to square root of 2. So by principle of mathematical induction, this result is true for all values of n. So we prove our result is this inequality is true. Now let's show that this sequence is a monotonically decreasing sequence by computing this term xn plus 1 minus xn. This is simply xn is 1 half xn plus 1 over xn minus xn. If I simplify this one, it's going to be a 1 half xn plus 1 over xn. And again, if I make the same denominator, this is going to be a 2xn, and this is going to be a 2 minus xn, the square of that term. So since we have the inequality that xn is always greater than or equal to square root of 2, it means x square is always greater than xn square is always greater than 2. So if this quantity is greater than 2, it means this whole entire quantity is less than or is equal to 0. So therefore, this inequality holds. So this term is always negative because xn square is always greater than or is equal to 2. And this is coming from this inequality. And this shows that xn plus 1 is less than or is equal to xn for all values of n belong to the set of natural number, or this shows that this sequence is a decreasing sequence. So we showed that our sequence is a bounded sequence and is also a monotonically decreasing sequence. Therefore, by monotone convergence theorem, this sequence is a convergent sequence. And we already computed that what is the limit of this sequence. So this complete the proof of this example. This is also the end of this video. Thank you very much for watching. I will see you in the next video. Bye for now.